Hello everyone, we are on chapter 4 about general vector spaces. Today we're going to be talking about section 4.3 on spanning sets. So just a quick review of where we are. We're on section 4.3 spanning sets. We're going to be covering all the sections through 4.6 dimension. We're going to be skipping change of basis, and then we're going to be continuing on with 4.8 and 4.9. So the objective of this section is that it's often the case that all of the vectors in a vector space V can be expressed in terms of some small subset S of vectors in V. The vectors in S can be viewed as the building blocks for constructing all of the vectors in V. So this is important because it makes it possible to deduce properties of an entire vector space V by focusing attention on this small set of vectors in S. So if you think about it, in 4.1, we learned all about vector spaces, specifically real vector spaces, and we had those axioms 1 through 10 that we had to prove. And then in 4.2, we learned about subspaces. And so what was interesting about that is that for subspaces, we knew about the properties of this vector space that it was in. And so we could use the properties of the vector space to describe the subspace, and the subspace obviously inherited some of those axioms. And so we could define that subspace and determine if it was a subspace by looking at axiom 1 and 6. But interestingly, here in this next section about spanning sets, what we're going to be looking at is this small subset S. And we're going to be looking at it in terms of, it's going to be important because we're going to be able to actually deduce properties of the entire vector space V by now focusing on this small set of vectors in S. So a lot is going on here. So we have 3 different concepts now for these different sets of spaces and how we're going to be defining them and what's going to make them a space, a subspace, or a spanning set. All that kind of information is going to be discerned. So before we look at spanning sets, I did want to cover really quickly a concept about linear combinations, because that's going to come into play for our definitions of what a spanning set is. So let's look at the definition incorporating linear combinations. So if you look at definition 1 in your section 4.3, it says if W is a vector in a vector space V, then W is said to be a linear combination of the vectors v1, v2, all the way through vr in V, if W can be expressed in the form W equals the sum of the v1, v2, all the way through vr multiplied by its scalars. So where k1, k2, k through kr are scalars. So these scalars are called the coefficients of the linear combination. So we've actually seen examples of this before. So I'm going to refresh your memory a little bit here. So when we're looking here at linear combinations, I want you to think first in terms of R2, so two-dimensional space here. And so here we'll have our usual Cartesian coordinate system. And here we have, you're probably familiar with this. Hopefully you remember your standard unit vectors. So for R2, we'll say that our set of standard unit vectors is going to be equal to the set v1 equals 1, 0, and then v2 is going to equal to 0, 1. And so hopefully you guys remember that. So here they're along the x and y axes, so this will be like v1 here, this will be v2. So these are your set of standard unit vectors. But let's say that you have, some other vector in this coordinate system. Let's say we have this vector W. Here it reaches this point A, B. Well, we could say that this vector W is a linear combination of the standard unit vectors. So we could say that W equals K1 times V1 plus K2 times V2. And what would happen is these coordinates here become the vector coefficients here. So this A would become K1 and this B here would become K2. And so that's the relationship between the coordinate system and this vector notation here. And so you can easily see, well, okay, this W is going to be definitely affected by whatever K1 and K2 is. So here it looks like, oh, if you drew this down here, maybe this K1 might be like 1.5. Here it might actually just be 1. But, obviously this coordinates would give a hint as to what these scalars should be, because, obviously W could possibly be one that goes way up here. And then these coefficients here would be larger numbers. You could also think of it, too, that these K1, K2 could be negative numbers, if W ended up being this way. But basically, this is the relationship here. So that vector W can be a linear combination of the standard unit vectors. Now, this is the simplest example if you're using standard unit vectors, because they're probably the easiest to visualize. Because you'll be able to see, how much the K kind of affects the length of W if you're using the standard unit vectors. But just realize that, V1 and V2, they don't have to be the standard unit vectors. I mean, you could have, certainly V1 could be something else. V2, like V1 could be, 2, 0, V2 could be 0, 2, what have you. But this is the relationship here. So you want to kind of think about what these linear combinations mean. So now that we've kind of explored linear combinations a little bit, let's go ahead and look at this official theorem here. We have theorem 4.3.1. It says if S equals a set of vectors W1, W2, all the way through WR. So if S is this set, it's a non-empty set of vectors, so that's key there, it's non-empty, in vector space V, then the set W of all possible linear combinations of the vectors in S is a subspace of V. So don't forget it's a space within a space, so it's a subspace of V. The set W in part A is the smallest subspace of V that contains all of the vectors in S, in the sense that any other subspace that contains those vectors contains W. So W is going to be all the possible linear combination of those vectors in S. And so that set W is going to be the smallest subspace of V. So any other subspace that might be larger, it's going to contain that W though. So W is going to be the smallest subset of V that contains all of the vectors in S. All right, so keep that theorem in mind. So to illustrate this concept, we're going to go ahead and do problem 3 in 4.3. And let's see, what does this problem says? It says, which of the following are linear combinations of, and then it gives some different matrices here. So which are linear combinations of, and then they say matrix A equals 4, 0, -2, -2, and then we have B here, which is 1, 2, -1, 3. And then they have C is 0, 1, and then this is 2, 4. And so they're asking in part A, that's the first part, they're asking is, okay, is this matrix 6, -1, -8, and -8, is this a linear combination of those three matrices above? So if we were to write this as a linear combination, we'd be asking ourselves, what, does this matrix here, does it equal K1 times our matrix A plus K2 times our matrix B plus K3 times our matrix C? So how do we solve this? So hopefully you remember from a previous section that we can write this as a set of linear equations. So here we would have, if we look at this, 4K1, so that would be here, this 4 here of matrix A, so this is B, that one's C, plus 1 K2 from our matrix B, and then we have plus 0 K3 from that matrix C, and all of that is going to equal this first entry here, 6, and so then creating the rest of the equations, we have 0 K1, let's see, what's the next one? Oh, that one's a -1, so this would actually be minus K2. And then we have plus 2K3 equals, looks like -8. And then we have -2K1 plus 2K2 plus K3. 1K3 equals, and we have that would be equal to -1. And then our last one is going to be negative 2k1 plus 3k2 plus 4k3 equals our negative 8. So there is our set of linear equations. So what are we going to do? We're going to solve for k1, k2, and k3. Those are going to act as our unknowns in this particular system. So I hope this is looking familiar because we've looked at this matrix here and we're trying to determine if it's a linear combination of A, B, and C. And so we can write this out as a series of linear equations here, and then hopefully this looks familiar, that we know what to do with this from our previous sections. So hopefully you can use your matrix operations then to solve for k1, k2, and k3. So the first thing you would do is take these linear equations here and we'd put them in matrix form. So certainly we'd end up with a matrix then that looks like this, our augmented matrix. So 4, 1, 0, 6, and then we have 0, 1, 2, negative 8, and then we have negative 2, 2, and then 1 and negative 1, and then this last line, negative 2, 3, 4, and negative 8. So here would be our augmented matrix that we would be using to solve this for k1, k2, and k3. And so we'd get that into, for the sake of time, we'd get that into reduced row echelon form. So you'd end up with a final matrix looking like this. So 1, 0, 0, 0. We've got 0, 1, 0, 0. We've got 0, 0, 1, 0. And then we'd have 1, 2, negative 3, and 0. This is the negative 3 here. Oh, pen's got a little heavy on it. So from this, you should be able to easily see that we had more equations than we did unknowns. So this last row here is all 0. But from this third row, we can see that k3 equals negative 3. From this second row, we can see that k2 equals 2. And here we can see from this first row that k1 equals 1. So therefore, we can surmise then that this matrix here that we are given in part A is indeed a linear combination of A, B, and C. Now, before we move on to the next part of the problem, I just wanted to remind you that linear systems will obviously have, if you remember from previous sections, it will either have 0, 1, or infinite numbers of solutions. So keep that in mind. So if we look at part B, and here we have a 0 matrix, and we want to know if this is a linear combination of the matrices A, B, and C. Well, I think that one's going to be pretty easy to write out here. So we've got k1, and then we had 2, negative 2, 0. This was our A, and then we have k2, and here is our B. 2, negative 1, 3. There's our part B. And then plus k3 times our C, which is 0, 2, 1, 4. And I think we can all see quite easily how k1, k2, and k3, if they're all equal to 0, that we would then get this 0 matrix. So here in this instance, that would be a solution, and we could say that this matrix here, this 0 matrix here, is indeed a linear combination of A, B, and C. So that one's easy enough to kind of recognize. Then we've got part C, and that looks like it is negative 1, 5, 7, 1. So we'd go ahead and set that equal to k1 times our 0, negative 2, negative 2, and that's going to be our A. And then we've got our k2 times our matrix B. And we've got our k3 times our matrix 3. So then you'd want to write this as a system of linear equations. So we'd have 4k1 plus 1k2 plus 0k3 equals negative 1. So here you can see this. This is the 4k1. This is the 1k2. And then there's the 0k3. All of that equals the negative 1. So our next one would be 0k1 plus, oops, this one should actually, I should just make sure I look at it before I just immediately write the plus sign. So minus k2 plus 2k3 equals 5. Then we have minus 2k1 plus 2k2 plus 1k3 equals 7. We got one more. And we've got negative 2k1 plus 3k2 plus 4k3. This time it's going to equal 1. So as you can see, we're going to be solving in this instance for our scalars k1, k2, k3 as our unknowns. And so we're going to get the, obviously, the augmented matrix here of 4, 1, 0, negative 1. We've got 0, negative 1, 2, 5. We've got negative 2, 2, 1, 7. And then we have negative 2, 3, 4, and 1. And so obviously you're going to use your matrix operations to get it into your reduced row echelon form. And so you should end up with the final matrix in reduced row echelon form is going to look like this: 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and then we have 0, 0, 0, 1. So hopefully you looked at this last row, realized that something is wrong. How can all these values be 0 and it be equal to 1? So how can 0 equal 1? So this is going to be inconsistent. And so we would conclude for part C that this matrix here is not a linear combination. So that's basically how that goes. So after we've done problem 3, let's go ahead and look at our theorems one more time, since we've explored linear combinations. So just to reiterate, theorem 4.3.1 says if S is the set of vectors W1, W2, all the way through WR, so if S is a non-empty set of vectors in a vector space V, then A, the set W of all possible linear combination of the vectors in S, is a subspace of V. So here you got the set S. Then the set W is going to be the set of all possible linear combinations of S. And then you have your subspace V. Subspace of the vector space V. And then for part B, we have the set W, and part A is the smallest subspace of V that contains all of the vectors in S, in the sense that any other subspace that contains those vectors contains W. And then it's important to note that the subspace W in that theorem that we just looked at again is called the subspace of V spanned by S. So don't forget this subspace W is going to be all the linear combinations of that set S. So this subspace W is called the subspace of V spanned by S. The vectors W1, W2, all the way through WR in S are said to span W. And we write that W equals the span of those vectors in S, W1, W2, all the way through WR. Or we could abbreviate that and say W equals the span of S. So obviously in the case where S is the empty set, it will be convenient to agree that the span of that empty set is going to be the empty space here. So remember this terminology here. So W equals the span S. And what is W? W is the set of all possible linear combinations of the vectors in S. And it's a subspace of V. Okay, so W is a space in a space, so W is in V, and W is a set of all linear combinations of S, so we would say that it is spanned by S, so those vectors in S are said to span W, and we write it like this, so W equals the span S. So you're going to want to review those two slides time and time again to make sure that you get all of your terminology right and you have an idea of what's happening. We've got this big vector space V. We're going to use our axioms 1 through 10 to determine, yes, it is a vector space. Then we'll have a space within a space. So usually we say W is usually how we denote the subspace. We confirm if W is a subspace or not by using our axioms 1 and 6. And then we obviously have this other definition here where W is, the set W is all possible linear combinations of another set S. And we have it, we call it W equals the span of S. Or we would say that the subspace W is spanned by S. So definitely review those slides. Okay, so moving on. We're not going to cover everything in this section, But we're going to go ahead and look at example 2 because it has a nice geometric view of spanning in R2 and R3. So let's look at part A, and it says if V is a non-zero vector in R2 or R3, so here we're looking here, that has an initial point at the origin, then span V is going to be the set of all scalar multiples of V, so this whole line here, and it's going to be the line through the origin determined by V. So here we have V, and then here we have span V also going through the origin, and so it's going to be all of the multiples of V. And so if you look at this KV, then, it could be anywhere. It could be here, it could end here, it could end here. So it just depends on what that value of K is. So certainly K also could be negative, so that means KV could lie along this portion here. But that span V is going to be all the vectors that are multiples of V. So this would be the span V. Once again, notice that V has an origin, has an initial point at the origin, and just realize that the span of V goes through the origin. Those are things to kind of remember there. Let's look at part B. So here is part B. So it says if V1 and V2 are non-zero vectors in R3 that have their initial points at the origin. So here we have the origin. Here we've got V1 here, we've got V2. And so the span of V1 and V2 would be all the linear combinations of V1 and V2. And it's a plane, see this green plane here? It's a plane through the origin, determined by these two vectors. So this span, though, is going to be all the different linear combinations, though, of V1 and V2. So certainly here's another linear combination. You have V1 and V2 multiplied by these scalars K1 and K2. So you can see here's K1 V1 and here's K2 V2. And then obviously that's their resulting vector K1 plus K2 V2. It can fall at any point in this plane because it's really just going to depend on what are the magnitudes of K1 V1 and K2 V2. So this is where these two vectors end, but what if they, kind of ended here and in here? You'd end up with a different K1 V1 plus K2 V2. And if these extended just a little bit out and this one extended a little bit out, then you'd have your other sum somewhere up here. So just realize it's all the different linear combinations of V1 and V2 depending on what your scalars K1 and K2 are. So it could fall at any point in that plane by adjusting those scalars K1 and K2. And don't forget, obviously, your scalars can be negative, so you could end up with the sum somewhere over here, as we saw with in R2 over here. So just to reiterate, if you're talking about R2, then you're going to be talking about in 2 dimensions, you're going to be dealing with a line. Keep in mind this line, this is going to represent span V. It's going to be a line through the origin. It's going to be determined by V. If you're talking about R3, certainly the span of V1 and V2, it's now going to be a plane through the origin. It's going to be determined by V1 and V2. I encourage you to look at example 4 about linear combinations again. And this will show you that you can write linear combinations in different ways. So before in problem 3, we had looked at, okay, hey, is this matrix that we're giving you, is it a linear combination of those other matrices? Well, in this instance, now we're given a vector, and it's described by its components, and it's asking, okay, are these other vectors a linear combination of it? So here it's asking about, let's see, it says, consider the vectors u, which is shown by its components 1, 2, and -1, and we have v equals 6, 4, and 2 in R3. It says show that w, 9, 2, 7, is a linear combination of u and v. So we do this very similarly to what we did in problem 3 with the matrices. So we'd kind of set up our equation here. We'd have 9, 2, 7, which is our w. And we're asking, is this a linear combination of our u and v? So we'd have k1 times our u, which is 1, 2, -1. So that would be our u up here, plus our k2, which is our times our v here, which would be 6, 4, 2, and that's our v. And so then we could kind of further simplify this. We know how to add vector components like this. So we could go ahead and then rewrite this to say 9, 2, 7, which is our w, equals our k1. So that's this k1, so it's multiplied by each of these components, and then we're adding this vector and this vector together. So we'd have k1 times 1 plus k2 times 6, so 6k2 here. That would be the first component for the sum of those two vectors. Then we'd have 2k1 for the second component here of u, plus the second component of v, that'd be plus 4k2. So that would make up the sum of our second components. And then we'd have negative k1 plus 2k2, and that'd be the sum of those third components. And so you could see here how then we can basically then write our different equations from that. So here we'd have for our first components, we'd have k1 plus 6k2 equals 9. So that's this one would be equal to these first components here. Then we'd have 2k1 plus 4k2 equals 2. And then we'd have negative k1 plus 2k2 equals 7. And then from there, you're basically going to, use your techniques that you have from previous sections to solve these systems of linear equations. You do these, we could do these by augmented matrices and then reducing them. You could do back substitution, whatever you judge to be the best way to get to the answer. But basically, you'd be able to solve this, and you'd get k1 equals negative 3, and you'd have k2 equals 2. And so obviously there is a solution to this system of equations. And so you'd be able to say, yes, our W is a linear combination of U and V. So let me go ahead and let's find a good example that we want to make sure that we do. So I wanted to draw your attention to example 5 because it has a little bit different wording, and now you're going to kind of see where these linear combinations come into play. So with example 5, it says determine whether the vectors v1, v2, and v3 span the vector space R3. So we need to know, is there some linear combination? Is there a linear combination of these vectors? So that we could say that these vectors actually span R3. So if there is no linear combination, then they do not span R3. So we would basically be using the technique that we did in the previous example. So we've got to find whether we can find some sort of arbitrary vector B, and we'll denote it like this, B1, B2, B3. Can we find some sort of arbitrary vector that is a linear combination of V1, V2, and V3? So if we can't find a linear combination, then we don't have, remember that subspace W, that's the set of all linear combinations, and it's a subspace of the vector space V. We're not going to be able to say that these vectors span the vector space R3. So just like in the other example 4, we would express these as a linear combination. So here we'd have that B equals K1 V1 plus K2 V2 plus K3 V3. And then if you're going to fully kind of like write that out, they have, obviously, with all their components. We'd have the components of B here. That's going to equal K1 times 1, 1, 2, and that was your V1 here. Plus K2 times 1, 0, 1, and that was your V2. Plus K3 times your V3, which was 2, 1, 3. And so basically then what are you going to do? You're going to set up your linear equations, and then you're going to use your techniques that you know in order to solve it. I will say that it might not be as easy as just, doing reduced row echelon form. You may very well need to dig deep, and so I encourage you to look over this example 5 and also review your theorem 2.3.8, which gives you a lot of your equivalence statements about matrices that's going to come into play. So everything you've learned before is going to now start to matter when you're trying to determine these things. So definitely review that. Have theorem 2.3.8 handy. I did put it here on the slides for you, so it is in this section if you do need it. But basically you'd be using parts of theorem 2.38, and you'd be making some determinations about the coefficient matrix that you come up with, and you'd be able to say, well, you know what, there's a non-zero determinant. It has a determinant of equal to 0, and so because of that, those vectors do not end up spanning R3. So a lot of things can go on with these problems. So that brings us to kind of some different rules or a procedure for identifying spanning sets. So you want to also kind of bookmark this slide because it's got some good steps for you to remember. So step 1 would be let S equal W1, W2 through WR. Be a given set of vectors in V, and let X be an arbitrary vector in V. And so step 2, you would set up the augmented matrix for the linear system that results by equating corresponding components on the two sides of the vector equation. So we've done that. So basically we're picking this arbitrary X and we're kind of determining, is it a linear combination of the vectors in set S? And then step 3, like I said, you're going to want to pull together now all your different techniques from chapters 1 and 2 to figure out if the system is consistent or inconsistent. So can you get solutions for your K1, K2, all the way through KR, however many it goes up to? Can you get solutions for each of those? Are those solutions where you either have no solution, or you have one solution, or you have infinite many solutions? So keep in mind those things. So if it is consistent for all choices of x, the vectors in S span V, and if it is inconsistent for some vectors x, they do not. So you're going to want to think about the results that you're getting. So it has to be consistent for all choices of x. So they're going to be writing in this arbitrary vector x. Is it going to be consistent for any value that you might put, values you might put in for the components of x? And if so, the vectors in S will span V. So like I said, I have put in theorem 2.3.8 for you. So you're going to want to look at this again. So just realize when we go to example 7, you got to remember there's all different forms that we might create linear combinations from. So before, in the other example, we saw the set S was a set of vectors and they were listed according to their components. Now, in this one, example 7, what do we have? We have got a set S of vectors that are now matrices. So here we've got to say for each of these parts, determine whether the set S spans M22. So this is going to be a set of 2 by 2 matrices, and is it going to span M22? So keep in mind, we've got to, if we're following those steps before, we've got to figure out, okay, is there an arbitrary vector x in V that's going to be a linear combination of these vectors in S? So if we look at A, I'm just going to write the beginning part real quickly. What are we doing? We have our arbitrary vector x, and so we're going to put it in more generic form. So we're going to say that it is just something easy like A, B, C, D. So we're going to ask ourselves, is this a linear combination then of these vectors in set S in part A? So, is it equal to K1 times our first matrix here, 1, 0, 2, 1, plus K2, 1, 0, 0, 1, plus K3, which would be 1, 1, 2, 0, plus K4, 1, 1, 1, 1. So just realize you would want to rewrite all of this, use all of your different techniques that you know how to use. You would hopefully try to get it to a matrix where you could use matrix properties to help you determine this. So definitely go through example 7 and see how they worked it. And so you will want to determine, does this set S span M22? And you're going to be making use of this arbitrary vector x, which has the form of a matrix of A, B, C, D. So check out example 7. I think there's only one more thing we kind of have to take note of for this, for spanning sets. This is some additional information, which is interesting. So looking at theorem 4.3.2, so if S is a set of vectors V1, V2, up to VR, and S prime is a set of vectors W1, W2, etc. And so if they're non-empty sets of vectors in a vector space V, then the span of S here, it's written out here with all its different vectors, it equals the span of S prime, and so here it's written out in all its vectors, if and only if each vector in S is a linear combination of those in S prime, and each vector in S prime is a linear combination of those in S. So this is a nice added little theory. So here's going to be the relationships between two sets of vectors, and you can make some conclusions that the span of S equals the span of S prime if it meets these conditions. So one's going to be where each vector in one is going to be a linear combination of the vectors in the other, and vice versa.